Thank you. So, yeah, so what I want to talk about today is a bit of continuation of what we saw with Mirta, which is nonlinear optics. And in particular, I will focus on what was kind of ignored by Mirta or pushed away, which is what happens when you use very intense lasers, okay? So, I mean, what I want to first talk, I mean, this is of course something we already see, is how we are kind of, if you look at the experimental community and theoretical community, moving a bit forward in terms of spectroscopies from kind of traditional spectroscopies toward what is called ultrafast spectroscopies. So I will just give you a few hints and maybe repeat a bit what was said already, but talk about that. Then I will explain a bit, or say, give you a feeling of how you describe and what is strong field physics in atoms, because intense laser physics in matter started historically in atoms and molecular gases. So it's very important to understand how you explain these simpler cases than solids, and also what is the mindset of people doing the actual experiment and driving the community. So this is what I will explain here. And then I will move toward what is sort of my main domain of research, which is intense lasers in matter, and especially what is this high harmonic generation in solids. So, as you know, and you have seen this a lot this school already, spectroscopy are already challenging for theory. Even if you do linear response, we have to describe complicated things like absorption of matter, for example, electron energy loss, and these are things that can be complicated. You have to take into account many effects, excitons, and so on. So this is already a challenge for us. But what happens when we want to do beyond linear? So what Mirta already explained us is that if you apply a perturbation to a physical system, you get a response. And if this perturbation is an electric field, usually you would say that the response is a polarization. If you want to translate this mathematically, what you can write is that the response of the system is expanded in terms of power of your perturbation. Here, my electric field. This is a very general expression. In fact, this is a mathematical series. It goes to infinity here. And in the series, what we saw is that the first term is a response proportional to the perturbation. This is a linear response. What comes next is what we call the nonlinear response. So far, you already know that. And what I will tell you now is that this is a mathematical series which has a finite reduce of convergence. What it means is that it only converges if you have weak laser fields, which usually in solids would be intensity of the order of 10 to 11 watt per centimeter square. What this means when you are in this so-called perturbative regime, what it means when you are in this perturbative regime is that if you look at the first order response, it is much more important than the second order or third order response and so on. And this is why you can speak about the physical meaning of the different orders independently. So you also already know that what comes from the first order response, for example, give you the absorption of light, refraction, energy loss, or transport. While if you go towards, say, second order effect, you find, for example, the second harmonic generation, but also optical rectification, and so on. So if you are in this perturbative regime, because you can treat each of the order and neglect what comes next, you can associate a meaning to all these different susceptibilities. But now what happens when you have an intense laser? Then this will not be a converging series anymore. What it means is that you will not be able to talk about a specific order without neglecting the others. You have to treat all of them into account. And this is called the non-perturbative regime. And this is exactly there that you are when you do strong field physics. Okay? And why is it important? Because if you are now in this regime of very intense lasers, you will only do the phenomena that are related to strong field during a fraction of your optical cycle. You have a laser pulse that oscillates in time, and if you have a very intense laser, you will only reach a critical electric field strength during a fraction of the period, which means that intrinsically we will localize in time the physics during a fraction of the period of the laser. And if you now put the numbers, visible light is around 1 eV. I mean, the titanium sapphire laser, 800 nanometers, is 1.5 eV. So if you look in terms of time, this 1 eV corresponds more or less at a femtosecond time scale, 10 to minus 15 femtosecond. Now, if you are doing a physics, a phenomena during a fraction of your optical cycle, again, 800 nanometers would be 2 femtoseconds. You are at a fraction of a femtosecond. You are reaching what is called the attosecond timescale, 10 to minus 18 seconds. And this is extremely interesting because all the phenomena we experience in our life, biological reactions, chemical reactions, physical phenomena, they start at this timescale. They are initiated there. You have the coherent motion of the electron in the bands or in the shell of the atoms, but also all the collective motions, plasmon, charge transfer, are initiated there. And the goal of this ultrafast spectroscopy are usually to target understanding what happens at this early stage of all of this. And using intense lasers is a way to achieve a very localized in time approach for this. And when I talk to ultrafast spectroscopies, there are, of course, many things you can do. So we already saw, time-resolved RPS. This was presented nicely by Selene earlier. And this gives you access to, for example, K-point resolve information. You can see, for example, here, a cut of the bands in the Brillouin zone. This is a KY axis, for example, here. And you see energy resolution. And you can see this for different points in time. Usually you have the order, in the resolution of the order of probably one snapshot every, say, 100 femtosecond, more or less. Depending, of course, on the experimental setup, but this is where you go. You also have other techniques, for example, transient absorption spectroscopy. And this is a very powerful technique. And this is also what people advertise a lot, for example, in this review here, where the title is interesting. What will it take to observe processes in real time? What they mean here is electronic processes. And what they mean by real time is that you look at the energy resolve information, and from that you can retrieve what happens in real time. And if you look at what was possible to achieve already in 2014, you can look at this plot. So I'm sorry you cannot read the labels, but this is the transient absorption for something as simple as an helium atom. And there, what you can achieve is a resolution in time, which is here from minus 50 here to plus 40. So you have here less than 100 femtosecond axis length. And the resolution, you see some oscillations around here. There are the oscillation of light at 2 femtoseconds I was telling you, because you drive here by a titanium sapphire laser. So you can really see what happens during a laser pulse, during an oscillation of the pulse. And if you look at the energy resolution, this is, at least in my opinion, quite fantastic. They start here at 18 eV, this is 28 eV, and you see a lot of structures. What you see here, for example, are the 1s to 2p transition. This is here the 1s to 3p transition, 1s to 4p, and so on. And here you would have your continuum of light. And you see what happens when the pump laser here hits your atom. And what you see are really a lot of dynamics. So I can just let you imagine what happens if you would do that in a solid, when you have many bands, many effects, and so on, many quasi-particles, and so on. So that's one approach for ultraviolet spectroscopy. That's for another. And there is a last one, which is what I will show you. This is something a bit emerging. We are clearly far from this type of fantastic result. This is doing high-harmonic generation in matter, okay? So now let's a bit have a look of what is this high-harmonic generation more in detail, okay? So for that, I'm just taking here the simplest system you can imagine of. It's an hydrogen atom. One electron in a potential, so you can write your Hamiltonian, kinetic energy part, the potential energy, and you can solve this. It gives you the energy levels. You all know that. The ground state is here, minus 13.6 eV. And then you have the other energy levels, and you have the continuum. So now, imagine that I want to put a laser on top of this material. I have my 800 nanometer laser. This is 1.5 eV, and I have to reach 13.6 eV. So I have to pile up many, many photons, you see, to reach this. This is clearly not a phenomena that you will be able to do with linear optics, where you would just stop here, you would not do anything. Even second harmonic, third harmonic, you are really far from it. In fact, you need to go to this really non-perturbative regime to act and do something with your laser on the hydrogen atom. And what will you do? So if you put now your Hamiltonian and you add a time-dependent Hamiltonian with a perturbation, an electric field in the dipole approximation, just put E dot R, you can solve this equation. This is time-dependent Schrödinger equation, one electron, we can solve it. We know how to do this. And for example, you can ask the question, what is the light that this atom will radiate? For this, you can compute the dipole moment in time. So you have your time-dependent wave functions, you compute this expectation value, and you record that. Then you do the Fourier transform. And this will tell you what is the spectrum of the light that is emitted. At least as if you would be solving Maxwell equation. You neglect ear propagation effect and other things, but this is what you see. You obtain, if you do the simulation for 800 nanometers with an intensity here of 10 to 14 watt per centimeter square, it's a very intense laser. You don't put your hand in this laser, otherwise you have a hole. But this is what you would get. You see a few things. You see first very sharp peaks, and these sharp peaks are in fact odd integer multiple of the incoming laser. The linear response is this peak here. What you have here, the second peak, is in fact the chi-free response that Myrta showed us. And all the other effects are higher order susceptibility effects. And importantly, if you look at the structure, we are not in this perturbative regime. I cannot take that the third harmonic contributes much more than the 5 harmonic to my polarization. There is kind of a plateau here. This is called a plateau. And this is a signature really that you are in this perturbative regime. All of the harmonic orders here, from 3 to 30 something, will contribute almost equally to the signal. Then, of course, at some point you have an exponential decay because you cannot get infinite energy anywhere out of your atom. So this is what people call high-harmonic generation spectrum. You start with an incoming laser and you get many, many harmonics, high order. And if you think about the numbers, I go up to harmonics 30 something about 1.5 eV. So I've converted light from 1.5 eV to 35 eV. This is very interesting. And this is used commonly in experiment to generate very intense laser. You can go to, I think the record are more than 1 kilo eV generated from 1.5 eV. So you can go very high in the harmonic order if you have a laser intense enough. So now how do we understand that? You can do, of course, a full simulation, but what is the intuitive picture? And this intuitive picture, this is what was already, spoiled a bit by Selene earlier this morning. This is that we have this so-called 3-step model of atomic physics. So what it is, the idea is that if you look at the ion and the electron that you have in the ground state, this is a blue wave packet here. When you apply your electric field, you will modify the potential that binds the electron to the atom. Okay, and if you apply an intense enough laser, you see that this is a ramp here because this is E dot R. E dot R is just a ramp in space. You see that you will create at some point a small barrier here. And we know from quantum mechanics that we can tunnel through the barrier. So what you do is that even though we need in the energy picture many, many, many photons, in the real space picture, you just have a small barrier to cross. And this at some point will happen. So this is called tunnel ionization. That's the first step of this 3-step model in this picture. Then you end up by a problem of an electron, which is a free particle in an electric field. It's a typical problem. You have a Lorentz force, a charged particle, and you know what happens. The electron will move following what the electric field direction is. So it will go away from the parent ion. But of course, the electric field oscillates. So at some point, the direction of the field changes and will bring back the wave packet towards the ions. And what happens is that you can, of course, have a scattering of this wave packet on the ions. You can have a recombination. And simply by conservation of energy, all the energy that this wave packet acquires when it moved in the field and accelerate will be emitted as light, just radiative recombination. And this light that you emit is high-harmonic generation. Now, because you repeat this process periodically, every half cycle of your laser, you go away, you come back, you go away, you come back, you end up by emitting light periodically. And this is why, when you look at the spectrum I was showing here, you get only harmonic peaks, because you have a periodic emission every half cycle, and you get there only odd integer multiple of the laser. So this is why we get this structure. Yes. This is a source term of Maxwell equation, even classical Maxwell equation. So this is basically, if you would solve Maxwell equation, you get an electric field out of this classical light. It's not a photon as a quantized object, I agree with you, but you can still solve classical Maxwell equation. You do a combination. You go back to the ground state. If you look at, when you come back on your atom, when you are here, let's say, I mean, after the laser is gone, I mean, a large portion of your wave packet that goes in the vacuum is back to the ground state. At least, yeah, anyway, I'm not talking about the description that we can do in the simulation. Huh? It's just the intuitive picture. And if you look at the time when this was done, this was developed in the 90s, and the early spectra of harmonic generation are from the 80s. So that's something very, let's say, well established and well, well understood. Anyway, so what can we do with this? So let's just put this in practice. So imagine we have ionized our electron. What we can do is we can have now our classical charged particle in an electric field. This is a semi-classical description. So you can write, of course, Newton's equations. You have the acceleration given here. You have a cosinusoidal electric field. You can integrate this equation twice to get the position with respect to time of my classical particle. And this is a second order differential equation. So I need two initial conditions. And what you can do as a simplest approximation and say that you start from the parent ion here at 0, and you start with 0 velocity. This is how you get to this equation here. And in this equation, there is one parameter which I put as T0. This is in fact physically the ionization time, when I started my motion basically from the ion. So at the moment, I'm not telling you at all when I start. I'm just saying I have a charged particle which is classically in an electric field. It moves, and we can see what is the trajectory, basically. So now if you plot this equation here, for each of the possible ionization time, you can do that during half of a cycle of a laser here, because anyway, everything repeats periodically. So what you see is that if you start at the very beginning of your cycle, you have the green trajectories here. You start and you acquire slowly a bit of velocity and you go away. But you will not come back because you acquire, in fact, too much velocities. You start early, you get accelerated extremely far by the field, and you never come back at some point. If you start too late, this is the red trajectories, you will also leave your parent ion, but you will never be able to come back to this. So you will never be able to do this recombination, this last step of the three-step model in which you emit light. But there is a sweet spot, and this is this kind of brownish curve here, when you leave the parent ion, but the field, sort of your starting point, is such that the field can basically bring you back to the parent ion. Then you can emit this light. And this is, you can write the condition here. This is a return condition. You have this equation here, which has no analytical solution, but you can solve numerically. And this tells you basically a link between the ionization time and when you come back. But it also allows you to compute the kinetic energy at the return time. This is the energy you have acquired. And by conservation of energy, this is what determines the photon energy you can, the light you can, the energy of the photon you can emit. Not at all, because I mean, I will talk about solids later. I mean, here you have a real space picture when you are localized in real space, which also implies that in Fourier space you're fully delocalized. If you think about solids, you most likely have a wave packet which is localized in momentum space. So the description, you do it in momentum space and not in real space. I will show an example later. So anyway, so you can compute the kinetic energy at return time, and if you plot it for all possible ionization phases, omega t is a phase here, you see that there is a maxima to the curve. So there is one trajectory among all of these possible trajectories that come back to the parent ion that give me a maximum energy. That's what I expect to be the maximum energy I can emit from my phenomena, by semi-classical phenomena. And this you can express as, in fact, 3.17. That's a kind of a magic number. You can explain from much more quantum mechanical calculation, by the way. And this is given with 3.17 UP, where UP is this ponderomotive energy, which characterizes your laser. So now, let's compare this to the full quantum mechanical simulation. So I showed you the spectrum before, and I show you that there is a plateau that extends, and then we have a drop at some point. So now what you can do is you can put the numbers. The maximum energy that I can emit in my semi-classical description is the potential energy I acquired, which is ionization potential, plus the kinetic energy I acquired, 3.17 UP. So ionization potential in the hydrogen case is 13.6 eV. UP, you can put the numbers for the simulation parameter here, and what you end up is harmonic order 29 point something, and if I draw it, this is really putting this, it's not fitting it, I'm just putting the line as it comes. This is my semi-classical description. It matches almost perfectly the position of this. And this is just one of the beauty of this simple three-step model and semi-classical description. It explains many of the experimental observations extremely well. And this is also why this atomic physics has been so successful for strong field, because in fact, they converted all the complication of quantum mechanical understanding into semi-classical description. So just with the idea, simple idea of trajectories and Newton's equation, you can explain many of the characteristics of this. And there are many other things that you can explain. I don't have time to go there. But the key is that most of the understanding and the also new proposed experiments are based on this idea of trajectories. You can unbalance some of the trajectories and create some kind of interferometer. You can enhance some trajectories or remove some of them and so on. So that's how people in strong field physics conceive harmonic generation in atoms and molecules, just based on these trajectories. Now, what I want to talk is a bit what is more important. Yeah, please.
Right? And so you have used the argument of the expansion and blah blah. So response function is a fluctuation object, right? Fluctuation. Instead, in the semi-classical picture, fluctuations are zero because you go back to trajectory. They are completely on the two different sides of the moon.
Completely.
So, I mean, physically, is in the atom is really the electron doing what the Newton solution is?
In fact, yes.
If that case.
Now the point is the response function becomes a bit useless because you would have to use so many of them, and in this expansion does not converge. So you will never be able numerically to compute all of these high order susceptibilities. People who have tried, they just failed miserably. If you have to go to order 120 in this response function calculation, you cannot.
This means the fluctuation is so large that the coefficient is not so large that the Taylor expansion doesn't work. But this means
no, but this is exactly. Yeah, no, I mean the trajectory is a clear simplification. I'm not saying that the physics is only localized trajectories. It's a way to explain and get a simple understanding. Yeah, exactly. Yeah, but the point is this community of strong field is driven by experimentalists. And this is why I wanted to present that, because all the understanding and proposals are exactly based on that. No, I mean, it's a choice. Huh? The point is, it's also this idea of non-perturbative regime. The Taylor expansion does not converge. We are beyond the radius of convergence. We cannot make a calculation. It will not converge by definition. So it's why it's better to use other.
I guess that also the susceptibilities will be really depending not on the difference. Will not depend on difference of times, but because we are in a non-equilibrium regime, so we don't have T minus T1, T minus T2, and so on.
So what you would lose, I agree with you, is the translation invariance in time. So you will have a function of T1, T2, but not of T1 minus T2. But if you would have one laser, you can still have the translation invariance in time. But you still have a Taylor expansion that is not converging. So numerically, people who have tried in the 80s, 90s, they all failed. So people stopped really trying to do that.
So, sorry, I propose we let Nicola finish the talk and then we take some time to discuss.
Okay, perfect. Okay, so yeah, now I want to talk a bit about this harmonic generation solids, which I just wanted to know what we have seen is just that there are different types of spectroscopies, what is this harmonic generation and how it is sort of understood in atoms. So now, harmonic generation in solids compared to in atoms and molecules is a very, very recent field of research. So as I told you, harmonic generation in atomic gases started in the 80s, even slightly before. And if you look at harmonic generation in solids, it only started with this paper, which is from 2011. And there is a simple reason for that. It was believed up to this paper that you cannot reach intensities of the electric field high enough to go to the non-perturbative regime without damaging the material. Because that's a problem when you have a solid, which has not so large band gap, is that you will deposit a lot of energy if you have an intense laser. Especially if you have an 800 nanometer laser with 1.5 eV photon energy, you will drill holes in the solids, really, if you go to the intensities I showed you before. So it was really believed for a long time that you cannot reach this non-perturbative regime before damaging. And what happened is that over 30 years, there have been a lot of improvement on the experimental side, especially for having intense mid and long infrared lasers. And this is what has changed the game, because now if you have a 2 micron laser compared to 800 nanometer, you are depositing much less energy, and you can still reach a very high intensity of your laser. So this allows to apply intense laser fields without burning the material. And this is what people observed. This is in zinc oxide. This was in Stanford in 2011, as I said. And what you see are these peaks. They are not as nice as what I showed you in the calculation before, but it's a solid, so it has much more complexity and much more physics. But you still see these peaks here, and especially they managed to observe up to the harmonic 25 in zinc oxide. And this create a gigantic mess in the community of strong field, because suddenly everyone realized that the piece of matter that was lying on the board, they could use to do high harmonic generation. And this has a lot of possible interest because it might imply compact sources compared to, say, a gas cell, which requires vacuum, requires a lot of technology in a lab. If you have just a piece of matter in air, you can still get high harmonic generation, at least up to 6 eV. And really, I mean, this creates a huge change in the paradigm of strong field physics. And of course, people try to understand this. Huh? So the first kind of things you could saw in the publication was kind of trying to replicate three-step model in solids. And I will not comment too much on this kind of pictures, but people also propose things like trajectory pictures in real space. Like, oh, look, I have the electron leave from exactly this atom here, and then they go in real space alongside different trajectories given by my laser, and if they scatter on the neighboring atoms, the trajectory is less efficient. If it's not, it is efficient. That's kind of the view that experimentalists have on this kind of things. Huh? And I have to say it's a bit sad, because it's really completely killing every crystallographic and condensed matter physics for the last 400 years. Huh? So you see, you have this momentum space trajectories or these real space pictures, and then people also realize that, of course, if I apply intense lasers, I have a long wavelength, I can move my electron because, of course, it is steered by the laser. And it means I might be able to do kind of transport phenomena, but dynamically during the laser pulse. And if my laser is intense enough, I can even take an electron, say, for example, in this picture, starting at the gamma point, steer it up to the edge of the Brillouin zone. And it will go back because of periodicity from the other side. This is what was predicted by Bloch, say 80 years ago, probably. That are called Bloch oscillation. This is known for static electric field, and what was proposed is, oh, suddenly we can realize that because we have very intense lasers, so we can move the electrons very far in the Brillouin zone, and this is this possible dynamical Bloch oscillation. And people started to wonder how much this phenomena is dominating or not in what they measure. And they also started to discuss about interband transitions. This is what you have in perturbative nonlinear optics. If you have a gap, this is in fact the only contribution. But again, this community is driven mostly by experimentalists, and they do a lot of models. And then the question is, what is the minimal model I need to explain my experiment? So do I need to do a 2-band model, a 3-band model, 5-band model? There were really fights. Huh? Like you see, this is like from a paper in Nature, you see? And they explain that they need, in fact, in this paper, 3 bands to match the experiment. But the problem is that, of course, as you know from being in a ab initio community, if I need the experiment to build my model, I mean, I'm just doing kind of a fitting. You cannot really predict what would be the outcome of the experiment. And this is why we need other methods. And also another point is, in all of these possible explanations, you will see only independent electrons. There is no interaction here, apparently, in solids, according to these views. Huh? There is no quasi-particles, there is no phonon, just independent electrons that move in a frozen band structure. Like this textbook example, this here. You just freeze the band structure, you neglect any correlation effects, and this is what is supposed to explain. Yeah.
A flow-gate bands, not the original bands.
I entirely agree with you. I'm just saying, this is, again, I'm just presenting a bit of what is the mindset of the people. Huh? So that's really, I mean, what it is. So, anyway, it is, in any case, quite clear, I think, that modeling this is complicating for us. I mean, what we saw with the MIRTA, for example, is when you want to do nonlinear optics in the perturbative regime, you can only do interband transitions, okay? And this you can do by sort of computing first your ground state and then taking matrix element and then doing perturbative approach. But now, if we are in this non-perturbative regime, we are doing both interband transition and at the same time, during the laser pulse, we are steering the electron in the bands. So we have to, for a given specific laser, track the motion of the electron. We cannot just do a perturbative treatment. And this means we have to do real-time simulation, as was already explained by many people, because we have this coupled interband intraband motion, even if we have independent electrons. And on top of that, we would have to include everything like band gap renormalization, excitonic effect, and all this quasi-particle, whatever you can imagine of. But this is complicated, and this is expensive because you have really to do, for one given laser, one simulation, and you have to take into account all of these effects. Now, what is the quantity you want to look at? So what you want to look, what is measured in an experiment is an intensity that comes out of your signal, okay? And of course, the intensity is an electric field, square modulus of an electric field, so it means it comes from Maxwell equation. And if you look at Maxwell equation, at least within dipole approximation, what you see is that the source term is the time derivative of the current. So if you compute the current and its time derivative, it's equivalent to be what would be the electric field emitted by the sample if I would be solving Maxwell equation, just having a bare propagation in vacuum. This would give you, if you are in vacuum, you put this source term and you get the electric field, just there is a propagation phase. But as long as you look at the intensity, this is basically the emitted field propagated in vacuum. So we want to compute this electronic current. It's a bit different from the polarization that Mirta presented, and there is a good reason for that. The polarization is only the contribution from interband contributions. But if you have an intraband motion, you move within the bands, then you have you don't have a polarization, you have an intraband current. And the polarization relates, of course, to the current because the time derivative of the polarization is an interband current. So what is more natural if you want to model the strong field physics, when you have intraband motion and interband motion, is to compute directly the electronic current. And what you have is, if you want to compute your spectrum, what you take is just time derivative of your current, you integrate over the full cell of your system because you look from far away, you have a dipole response, you do the Fourier transform and you take the square modulus because you look at an intensity. So that's basically what you compute as an harmonic spectrum, let's say. Now, I have a small kind of exercise here to just give you a feeling already that what you can get, even if you do the simplest case you can imagine, one band in 1D. So there is no interband contribution, there's only intraband, and I will show you that you get the harmonics. So you can define the current as just the product of a charge times a velocity, okay? So that's a current. So now if I take the current from the full Brillouin zone, I just integrate here, and this is what I get. That's my total current. And I can make some approximation. I can assume that I have a infinitely localized wave packet. So I have a delta in K where are my charges. And I also have no Berry curvature in this example. So just the velocity of the electron is just the curvature of the bands. Then if I assume that I have independent particles, I don't have any other force that act on my electron apart from the electric field, then I get my trajectory that we were talking about. There's a trajectory in momentum space. And if I plug, you see in this expression here, I replace this guy by this delta. I have the curvature that I evaluate at K of t. And this equation here gives me what is K of t. If I start from, say, gamma, I know everything now. So now I can take a general band, which is a sum of cosine. And here you see this is from another Nature paper. This is a vision of experimentalists, again, of what is my band structure. I have a one band here, and I decompose that in many cosines, okay? So now if you plug all of this together, you get an expression here for the current, which is extremely useless because it is a sign of some factor here, which contains a block frequency and a sign of omega t. But you can use this relation here that the sine of x, sine of phi is expressed in terms of an infinite sum of Bessel function. And if you do that, you can rewrite the current in this 1D one-band case in this form here. And maybe you cannot read all the details, but here you have an infinite sum over one of the coefficient of the band structure, one over this Bessel function. You have a huge prefactor, but what is more important is you get naturally here a sine of not omega t, the driving laser, but 2s minus 1 omega t. You get here, in fact, your harmonics, odd integer multiple of your laser. They come naturally, even in this 1D model for the things. And what is also exciting for the experimentalists when they look at this kind of things is that this current here contains the coefficient of the band structure. This is why people want to retrieve, for example, band structure from high-harmonic generation, because the information is contained in there. It's of course integrated, and there is a lot of effort currently to try to take the information from the current or for the harmonic emission and to retrieve what is the information on the band structure. I will not show many examples of that, but this is just also further motivation to study the strong field physics is because you move within the bands, you basically acquire the knowledge in the emitted light about the curvature of the bands, and you might retrieve information about them. So now, how do we do the simulation? So what you do is you do real-time many electron dynamics with your favorite methods. In my case, this is TDDFT. You can also use Yambo and do any kind of many-body Green's function approach at different level. The point is you want to do a real-time simulation for a given laser to be able to compute observables like the electronic current. And this is what you measure. You adjust expectation value of P minus A divided by C. This is, say, gauge invariant current when you have your vector potential A here. And if you compute it, you will get something that looks like this. It usually starts to be very smooth and oscillating at the frequency of your laser. But during the laser pulse, you will see that it acquires anharmonicities. These are, in fact, this very fast oscillation are, in fact, my harmonic signals that builds up in time. Okay? And then what you do is you take this current, and you do the Fourier transform, you use this formula here, and you get an harmonic spectrum like this. So there you see, for example, this is for bulk silicon, you see many peaks. They are not very clear in this case because I was not propagating for a long time, but you see basically harmonic generation. One word of caution here is that the convergence is critical in this kind of calculation. The reason is simple. You want to resolve the many harmonic peaks. And if you look at this plot here, you see that I start from, I am in log scale here, and I cover almost 10 orders of magnitude, which means that your electronic current needs to be converged for 10 orders of magnitude. This is a much more stringent requirement than to do linear response or even second order. You need to be extremely converged to be able to resolve 10 orders of magnitude in your current. No? So you have to be prepared to the fact that these are complicated simulations. And the question you might ask is if this is working or not. And in fact, it turns out that for simple material like silicon, when you can sort of neglect a bit of all this many-body effect, you can get very good comparison with experiment. For example, this is a comparison we did with people in Hamburg, in the same building as me. There were some experimentalists who built an experiment for high-harmonic generation solids. They did the experiment for bulk silicon, and this is what they obtained for specific laser parameters. Okay, they obtained this black spectra. What I did was to do a simulation where I put a kind of advanced functional in this TDDFT business, which produce a correct band gap and a decent band structure. And what you see is that you can reasonably explain the experiment. And why is it so? Because you are here using a very intense laser, so you are shaking up a lot the electron. And in fact, this is what people in strong field community would call the strong field approximation. They assume that you have two terms in your Hamiltonian. One is the Coulomb interaction, one is the electric field, and they say, okay, the laser field is so intense that the Coulomb interaction becomes a perturbation with respect to the electric field. So this is why you can neglect many body effect and so on. This is, of course, reasonably correct for silicon, but it's absolutely wrong for the type of material and solids. Sorry? No, there is no adjustment here, 0 parameter. Of course, I choose a functional that gives me the correct bandgap, so I choose, I mean. No, but for functionals, no, I don't.
You're starting electronic structures, and you're channeling your potential in the evolution. Okay.
So now I just choose a meta GGA that gives me a wide bandgap for silicon and a decent band structure. And in fact, you can check that if you freeze the interactions, like R3N exchange correlation, which means you do an independent particle, and you compare the result, you get the same, which means that the band structure is basically not changing for silicon. But there are really a lot of cases where this is not true, which experimentalists still need to understand. And this is why we need also some of you to start working on this with correlated and many electron methods to also show that and explain that. Huh? Just to show you an example, if you go to strongly correlated materials, argument that Coulomb interaction is a perturbation compared to the electric field is just wrong. If you think about a bad model, you would have an on-site U interaction that describes the strength of electron-electron interaction, okay? You can compare that to the photon energy. And then you see that they are of similar magnitude. You have a U, say, in nickel oxide of 7 eV. You have a photon energy of, say, 1.5. You cannot say that the electric field dominates in terms of scale compared to correlation effect. And what happens is if you shine now in material like this, a very intense laser, you will renormalize electron-electron interaction. You see screening effects in time. So the way I did that is a poor man's approach to all the nice things that was shown this week. This is called DFT plus U. This is a local static self-energy, okay? You can really take the GW, start from that and make the approximation that you have a local interaction, that you have a static limit, and this you will end up by DFT plus U. But still, what you can do is you can let the screening evolve in time, and it means that the U might become or not time dependent. And what we found here in this paper is that if you apply very intense lasers, you can renormalize about U, which means you will have a dynamical band structure. And this, of course, has an impact on the harmonic generation. If you freeze the band structure, you get the red curve here. And when you let the band structure evolve, the screening renormalizes about U and the band gap, you get more intense harmonic emission. Of course, the band gap becomes smaller, so it's more easy to ionize and to put electron in the bands. So you clearly have effect, and you can probe this effect from, say, harmonic generation. Or at least this is the hope, that later you can turn that in a way to probe this. But at least you see a clear effect of the interactions. So now I want to finish with one very last application, which is something new we are working on. But I thought it was nice for this school to talk a bit about excitons. So the question is, again, can we see excitons in this strong field regime? So what we did here with one of my students was to do simple 1D R34 calculation. They are not made to reproduce any experiment or to explain one specific material. They're just there to look a bit at the physics, okay? So you take a nitrogen dimer chain, you put many K points in this Brillouin zone, you sample it, you converge the thing. And what we did is to do a pump probe experiment. The pump here is made to, for example, pump exciton and to prepare a finite population of exciton, or to pump just free carrier if you're resonant with a band gap. So the idea was to compare, to see if we can probe the effect of having a finite population of exciton or not in our system. So we did this pump probe settings. We pump particular excitons. We come with a probe that generates the High-harmonics. This is an intense probe here, which is 50 femtosecond. It's a 2 micron, or depend on the case. And we looked at what happens when you start to put excitons and how this changes the harmonic spectrum. And what we found, in fact, is that when you have the materials without any prepared population of exciton, you get a spectrum which has peaks. Fine, this is what we expect for harmonic generation. But when we start to put a population of excitons, we found a gigantic enhancement of a peak at the exciton frequency. But we also see appearing new peaks, which are in fact sidebands. They are exactly at the frequency of the exciton peak plus or minus 2 times the laser frequency. This is omega exciton plus 2 omega 0 of the laser. This is omega exciton minus 2 omega. In fact, if we look very carefully at the data, there are even more higher order sidebands, let's say, but here we don't see them really. Anyway, if you change your laser, you can really see these sidebands moving. So they really follow this omega exciton plus or 2 or minus 2 things. And the nice point is that we have really a setting here where we can plot the exciton wave function. You can define what is the number of local bond excitons we have prepared, and we can see a lot of things happening. For example, if we look at the intensity of these sidebands, we can see a strong correlation with respect to the number of excitons we prepare. So what it means is that this sideband's intensity is more or less proportional to how many excitons I have made in my sample. So I can really probe a finite population of excitons in my sample. So no virtual excitons, I have to prepare population to get them. Huh? But I can probe that. We also saw signatures, if you look at different observables related as of the Stark shift levels that appears in the how the harmonic signal builds up and so on. So we can see the Stark shift of the exciton. We have signature of exciton dissociation and recombination that appears. So there is a lot of things you can do. And this was my final example for today, that you can do with a strong field. You can also look at quasi-particles, okay? So just to summarize, I mean, I talked a bit about this ultrafast spectroscopy and how you want there in the overall picture to track the electron dynamics on their natural timescale. Then if you look at strong field physics, this is one way to do it. You can do this in atoms and molecules, and you explain that by this three-step model and these trajectories in real space. And then when you move to solids, you have to think about trajectories in momentum space. You have interband, intraband transitions, but it's also important to remember that you have all this many body effect in strongly correlated materials, for example. You also have quasi-particles, excitonic effect, like in this chain of hydrogen. And there are many more things. Huh? You can look at defects. We found that you can probe the defect because you have very strong local field effect when you have a defect, because you have an induced field that appears there, but important. You can look at quasi-2D materials, and you have a mixture of atomic and bulk response, because depending on the angles, you will put the electron moving in the bulk material or in vacuum. You can even look at liquids. This is interesting, or topology. There are many more things. And really, it's a new field, so there is really a lot of things you can do, and I think you should start also looking into that. And with that, I want to thank you for your attention.
So we thank Nicolas very much, and I'm sure there would be many questions also from the speakers, but I would say for now I take just questions from the students because we're running late. Okay, then yeah. Since it's a school, I would like to, I mean, if there are students, if you have any question. Yep.
Thank you very much for nice talk. Can you please comment on topology, why topology can be important in these things?
It's more the other way around. Can you use strong field physics to probe topology? So that's an open question.
In what sense topology? What
topology of the bands, Berry curvature effects, for example, this kind of things. You have topological protection of some features of the band structure, you know that.
Yeah.
And the idea is that, does it reflect or not in the emitted light when you have a strong field? Or do you just wash out all these properties? So it's an open question that people are looking now. Are the signatures of, if I have a specific, I'll say Dirac semi-metal, a Weil semi-metal, a nodal line, can I see signature of these things in the spectrum, in the harmonic emission? Because there you could be able to probe and do spectroscopy. Huh? So the idea is that are there specific features that would tell me if I send a very intense laser on a piece of matter, I have undoubtedly this is a Weil semi-metal because I see this or that feature. So that kind of question that people are asking. Can we turn this sensitivity that we might or might not have on topology as a spectroscopy tool? That's yeah.
Okay, thank you.